My name is Vicky Kaspi. I'm a professor in the physics department at McGill University and director of the McGill Space Institute. And I am going to talk to you about fast radio bursts, which is a new astrophysical puzzle, something that we've only really understood exists in the past decade and which we really don't understand. So this is a sort of an animation to just get you in the right headspace about what these objects are. So when I say fast radio bursts, what I mean is that there's these short bursts of light, and by short, I mean typically a few milliseconds, thousandths of a second, that are going off all over the sky all the time, and pretty often, roughly, we think around 1,000 times per day across the whole sky. And we really don't know what they are. Now, this picture that you're looking at is just to get you in sort of the right transient headspace. They come, they burst, then they're gone. But they're fast radio bursts, so we're detecting them not in the optical light that you're seeing right now, but in the light of radio waves, the sort that you've heard already about radio telescopes, but here's just another picture of a radio telescope here on the cover of a recent issue of Nature, the prestigious science journal, where we reported some of the results I'm going to tell you about today just earlier this year. One of the things that we do know about this phenomenon is that these bursts are almost certainly coming from very, very far outside our Milky Way galaxy. And in fact, we believe they're coming from cosmological distances. That is, from distances that are appreciable fractions of the entire size of the universe. Now, how do we know this? In astronomy, measuring distances is one of the biggest challenges we have, especially for objects, because something can be nearby and appear, you get some light from it, so it'd be intrinsically pretty faint. Or if it's really, really far away and you get the same amount of light, that means it's really intrinsically very bright. So determining the distance is crucial when you're trying to understand a puzzle. And when I'm telling you I think they're far outside the galaxy, indeed at cosmological distances, that's quite a statement. They have to be very, very, very powerful indeed. And so powerful, ubiquitous, and completely unexpected and unpredicted. Very interesting. Now, why do we think they're so far away? Well, it comes down to the fact that we detect from them radio waves. And when I say radio, you're probably picturing something like this. And indeed, this does detect radio waves, but it detects terrestrial radio waves. And one big difference between the way we use that device, the radio, and how we do radio astronomy is that when you want to hear some noise, and you want to listen to something on your radio, you tune it to a very specific frequency. So I don't know Toronto radio stations. In Montreal, if you want to listen to CBC, like I do, I turn to 88.5. If I want to listen to pop music, or rather my teenage daughters want to listen to pop music, they turn to 92.5. And the reason you don't hear White House press briefings at the same time as Beyoncé or Nicki Minaj is because you can tune to different frequencies, and the stations, they only radiate at those specific frequencies. But in astrophysics, sources, and particularly fast radio bursts, they don't emit at specific radio frequencies. They emit at all of them. And they emit at all of them at the same time. And we receive all of those frequencies at the same time. But not quite. Almost at the same time. And that's very important. So the first fast radio burst that was ever discovered, we call it fondly the Lorimer Bursts. I'll explain shortly why. And this is a technical plot of it, but judging from the questions at the intermission, you guys can totally handle this. First, look at the inset, this plot here, where you can see the burst. There it is. This is radio intensity versus time. So time is on the x-axis here. You see the burst of radio waves. That's what you should be picturing when I talk about fast radio bursts. But in the larger picture, you see what's actually happening. So time is still on the x-axis here, but on the y-axis, it's radio frequency. And a typical radio station would just be this. Actually, this probably is a radio station, very irritating, but some noise in our data, one line at all times at one frequency. But the fast radio burst actually comes in at all frequencies, but at different frequencies at different times, even though at the source it was emitted all at the same time. So what you can see is at the high radio frequency, so this is we call this a full band, a very wide band. At the very highest frequencies, the burst arrives first, and then it's delayed in a very special way. And this is what we call a propagation effect. Even though the source emitted the burst all at the same time, the radio waves are delayed because of stuff in the intervening matter, so in the galaxy, or in the intergalactic medium. And that stuff is free electrons. It doesn't so much matter, but there's stuff there that delays radio waves. And it's the degree of that delay, the time delay from when the pulse arrives at the highest radio frequency to when it arrives at the lowest radio frequencies, that's telling us that these objects are at cosmological distances. So an object that's really nearby, they'd all come at the same time. An object that is very, we call it dispersed, that where there's a huge delay, that means it's coming from very far away. And I can show you, first of all, I should just mention the Lorimer Burst was detected at the Parkes Radio Telescope in Australia, which has done a huge amount of the work in this field so far. And I promised I'd tell you why it's the Lorimer Burst. It's because, the astronomer who found it, his name is Duncan Lorimer. And there he is. Now, I said it's free electrons, and it's a little bit technical, but I think I want to show it to you. This is what a typical galaxy looks like. It's not our galaxy. You can't take a picture of your galaxy when you're sitting in it, just like you can't take a picture of the outside of your house when you're inside it. So I've taken a Milky Way-like galaxy, looked down on it. Now, this is a contour plot of our own Milky Way, where these the cross here is the center of the galaxy, and our sun is at that little white dot, over there. And there's some, schematic spiral arms drawn in there. But what all the other lines are, this is a contour plot. So I'm sure you've seen contour plots like relief maps, things like that. It's a contour plot of lines of constant a number of electrons. And so why am I telling you this? For any object, when you measure that sweep, when you measure the delay from the high frequencies to the low frequencies, you should be able to look on a map, and the greater the delay, the further away the object is. And we do this all the time with neutron stars, with radio pulsars that you're going to hear about from Scott Ransom later today. This is how we determine distance to these objects. We measure that sweep rate. But coming back to the Lorimer burst, in these arcane units, the maximum allowed by our galaxy in that direction for this delay here in these crazy units is 25, whereas the Lorimer burst was 375, over 10 times what our galaxy can possibly account for. That sweep rate, the degree of sweep, the degree of delay, it's impossible, as far as we know, to account for in our galaxy alone. And this is the major clue, the major reason we think fast radio bursts have to be extremely distant. Now, so as I said, it has to be way outside our galaxy because there's not enough electrons in our Milky Way to account for that sweep. And if it's way outside our galaxy, and if it's at a cosmological distance as we think, these objects have to be extremely bright intrinsically. And so this is the mystery. And what are they? We don't know. So what are fast radio bursts? Currently, and this is with great respect to my theorist colleagues, there are more theories than there are events that we've measured. So far, there's about a couple dozen of these events, mostly detected with the Parkes telescope. And so there's all sorts of ideas what they could be. When something goes boom in the sky, you think of an exploding star like Lars just talked about, or perhaps colliding neutron stars that we believe also happens in the universe. There's also ideas of comets impacting neutron stars or evaporating black holes. There's all sorts of interesting ideas, but the bottom line is we don't know. And you might say, well, if it could be an exploding star, why don't you just go and look? Why don't you commandeer an 8-meter class telescope on the mountaintop in Hawaii and just point it at the fast radio burst or where it happened and have a look? And I would love to do that. We would love to do that. The problem is that the radio telescopes like Parkes that detect these objects tell you it's sort of over there. In other words, they don't have very good resolution on the sky. They tell you roughly where it is, but if you were to look in that patch, there's 1,000 galaxies. That patch is just too large to know exactly where the fast radio burst came from. So without knowing where it came from, you can't see, did it even come from a galaxy? You can't know. But that's recently changed, so we're very excited by this. This is actually a catalog of all the known fast radio bursts, and I want to draw you, so I'm just showing you. You could Google this if you wanted to bring it up and have a look and enjoy some of these wonderful numbers. But I'm just going to circle one of them. That column is showing you the telescopes that detected the known fast radio bursts, and there's one in there that was detected not by the Parkes radio telescope, but by the Arecibo radio telescope, which is until recently the world's largest telescope in Puerto Rico. This is in Puerto Rico. It's about 3 football fields across, 300 meters across. You can see it's a few hundred meters there. I'll just point out, this is a catwalk. This is a catwalk, so if you want, you can walk from this. This is beautiful science center, Arecibo Science Center, wonderful. You can walk on this catwalk to the top. And in fact, there we are. That is me at the top of Arecibo, very exciting, standing right at the top of the catwalk over there with my colleagues Paul Ray from the Naval Research Laboratory and Maura McLaughlin from West Virginia University. And if you zoom in, yes, my knuckles are white. It is scary up there. Arecibo is also famous because it was featured heavily in the James Bond movie GoldenEye, starring Pierce Brosnan. And if you decide to rent that movie, you will see him running on that catwalk. But actually, it's not him. It's a stunt double because Pierce Brosnan was too afraid to run on the catwalk. And so I'm very proud to say I've done things James Bond was too afraid to do. But here it is. This is the fast radio burst that was discovered at Arecibo by our research group. And you can see here the telltale sweep. You have x-axis is time, and the y-axis, again, is radio frequency. And there you see it, high radio frequencies arriving early and sweeping through. And there it is once we've, in software, delayed all of this and corrected for the effect. And there's the burst. And this was very exciting because it was the first time that a fast radio burst had been detected at a telescope other than Parkes, which made everybody go, phew, I guess these are real, because if they're all detected in one system, it's a little... But yes, we've just definitely detected this. But that wasn't the end of the excitement with this object, because to our amazement, this object repeats. And you know, when you're trying to study a puzzle, you're trying to understand what these things are, this is a gift. And this was a surprise to us. We had looked... my colleagues at Parkes had looked at some of the spots on the sky over and over again, never seen one repeat. This one repeated. It took us months, actually. We would stare at it and nothing would happen. And then suddenly, one day, 10 bursts. And by now, we've seen many dozens of bursts. This got a lot of press. There it is. Paul Schultz was a PhD student, actually, who made this discovery. It was very, very exciting. And it's exciting because once you know where to look and you know that it's going to go off again and again, you can point a different kind of telescope at it. This is an array of radio telescopes called an interferometer. And using this kind of telescope, you can pinpoint very precisely where the object is. So spreading out a bunch of radio telescopes and using them all together lets you pinpoint on the sky exactly where it is. And so, you know, you want to go hunting for, you want to go fishing where you know you're going to catch something. And so that is what we did. And it took months. Again, this took months. We took that telescope called the Very Large Array, which is in New Mexico, and observed over and over again. Nothing happened. Finally, one day it went off. And you can see the burst here, the way the interferometer shows it. The black circles were the uncertainty regions prior to the VLA observations, just from Arecibo. And you can see here now it's pinpointed very, very precisely on the sky. And that was very exciting. So first, it's because of the repetition that we were able to do this. And with it pinpointed on the sky, oh yes, and this is, you can see with the VLA the same sweep, and it's exactly the same amount of sweep as expected, and there's the burst. And with that boom in the VLA, and actually we got 9 more booms with the VLA, so there was no problem, then we could go to the 8-meter telescope on the mountaintop in Hawaii. We went to the Gemini telescope immediately once we had this position, and we could go and see what was there. And to our amazement, so here is now the localized position, and here's the optical image where there is actually a very, very faint galaxy there. So in some sense, it's no surprise that the fast radio burst is located in a galaxy. But what was amazing is this is not the sort of galaxy we expected. You know, when you have an object like this, you expect it to be where most stars and most gas are located, which is in a big galaxy, and there's lots of big galaxies on the sky, but this is located, we call it a dwarf galaxy, something like a few % of the mass of our Milky Way. And right now, you know, sometimes science is kind to you. It answers some questions by giving you a repeating FRB. And then in other ways, it just opens more questions. Why would this event, this unique object, be located in so puny a galaxy? We just really don't know. But the good news is, yes, indeed, these objects are definitely at cosmological distances. Now that we've detected the galaxy, we can determine its distance very precisely. And indeed, these things really are cosmological. This is work done by McGill postdoc Sriharsh Tendulkar. And so this got quite a bit of press. Here was the New York Times. They made this little app showing how we localized it. And there's the Gemini image. And that flash is fake, obviously, because we didn't see it optically. And Dennis Overby wrote that it's probably, because we found it in a galaxy, it's probably ordinary physics. Like, ordinary physics? Like, I'd like to go to his house and bring an FRB in the middle of the night and set it off and see how ordinary he finds it. But it was very interesting to see the contrast and how these different press places reacted. This was the New York Times, ordinary physics. The New York Post, on the other hand, whoops. The New York Post said that it could be aliens. We did not say that. We do not think it's aliens. So where do we stand with fast radio bursts? At least one of these objects repeats. And clearly, colliding neutron stars or exploding stars, they can't do it over and over and over again. It rules out a huge class of models for these objects with just this one object. Now, it's only for that one object, and we have yet to see another fast radio burst repeat, even though we're looking. We're looking, and it does sometimes take months, so far we're scratching our heads. We should be seeing more repeats. We haven't yet. And it opens a lot of questions. Do all fast radio bursts repeat? Do all FRBs repeat? Or are there two classes, these that repeat, and this is two totally different phenomena? We don't know. And what is the bursting source? I mean, it just comes back to the repeater. It's producing a huge amount of energy, and over and over and over again. That's interesting. How does it do that? And why is it in a tiny little galaxy? So these are questions we don't know the answers to. We're thinking very hard about it. And one of the ways to solve the problem is to find more of them and see how many repeats. Are they all in little tiny galaxies? And we think we're going to be finding a lot more very soon using the telescope that Matt Dobbs described to you earlier today, which was originally designed for mapping hydrogen through the distant universe at cosmological distances and doing cosmology, but which turns out the same exact design is fantastic for detecting fast radio bursts. I don't think we could have chosen a better design, and that's because, as he explained, it sees a huge area of the sky at the same time. And for transient science, where you don't know where it's going to go off when, the best way to detect sources is to look at a large area all at once. And so I ask you to please stay tuned, because here in Canada, we're going to make a lot of headway on this problem very soon. We hope to be detecting, so I told you there's a couple dozen in the FRB catalog so far since 2007. We think we're going to detect a couple dozen per day with CHIME, and that'll give us a whole lot of new sources to study and understand. And with that, I thank the funding and agencies, and thank you very much.
Could I ask you a quick question, Vicky? If these are all at cosmological distance, does that imply that they happened a long time ago and that they aren't happening now, or now in the relative sense?
So yes, the ones that we detect, if they're at cosmological distances, they occurred a long time in the past. That's true. On the other hand, there's no reason to think that they couldn't happen in the more local universe as well. We have even given some thought to what would happen if one went off in our own galaxy. It doesn't seem impossible. It all depends what these objects are, how common they are, and how often they go off per galaxy. It's not impossible that they could happen locally as well.
Just haven't been seen locally yet.
So it's actually a really interesting question how you would detect it if it had happened locally, because one of the biggest problems we have in radio astronomy is terrestrial interference. And there's all sorts, your cell phones, satellites, everything makes all sorts of noise. And when we try and detect these objects, we're sifting through a ton of noise, and we throw out all sorts of signals that seem to us as coming, that are being just too bright to be real. So if there had been a local one, it's not impossible. We might have actually ignored it. And we are now thinking of ways to solve that problem without letting in the flood of cell phone signals and all that.